Hello, everyone, and welcome to the final session of CosmoPalooza 2023. I'm Anthony Cremeen. I'm one of the co-organizers of CosmoPalooza 2023, and I'll be the moderator of this update from the Dark Energy Spectroscopic Instrument collaboration. And so with that, I will hand it right off to Andreu, who will be giving the first talk. Please take it away.
Okay. Hi, everyone. I hope you can hear me well.
Yes.
And let me share my screen. Okay, hope you can see everything well.
Looks great.
Right. So thank you very much for this invitation. It's great to be here telling you about the Dark Energy Spectroscopic Instrument, or DESI. This is going to be the first talk out of 4. So I will give an overview and my colleagues will talk about the early science results. First of all, let me thank all our sponsors and all our participating institutions. So the big news is that as of last week, DESI is now 50% complete, which is really, really, really good news for us. So we started the survey a little bit more than 2 years ago in May 2021, and it was the first dark energy, stage 4 dark energy experiment to go on sky. So in a nutshell, DESI is a multi-object spectrograph with 5,000 fibers at the 4-meter Mayal telescope in Arizona. And here on the right, you can see the early data release. So this is data that was made public in June and that already contains a very rich data set with more than 1 million spectra. And here you can see the distribution of galaxies in some of the patches of the sky that we observe. So in this talk, I will start by giving an overview of the probes, the cosmological probes that lead the analysis in DESI. So the first one is baryonic acoustic oscillations, or BAO. We probably heard about this in this webinar in other presentations, but just to summarize it, those are acoustic waves in the early universe, in the photon baryon plasma, that we can see as imprinted in the distribution of mass, for instance, when we look at the cosmic microwave background. So these oscillations correspond to the scale of sound horizon. So this is how much all these waves travel between Big Bang and the recombination era. And the same imprint can also be seen at low redshift in the distribution of galaxies. So here I'm showing results of measurements of correlation functions of galaxies in the Sloan Digital Sky Survey, SDSS. So in the configuration space, these baryonic acoustic oscillations look like a sharp feature at 150 megaparsec. And we can use that as a standard ruler because we measure this feature at many different redshifts, and therefore we can see how the universe has been expanding. And here I show the measurements from 7 different tracers divided by the prediction from Planck in a lambda CDM universe. And you can see that the agreement is remarkable. The last point in this plot in pink or purple, this is from the Lyman alpha forest absorption in the spectra of high redshift quasars. And there will be another talk on this later today. The second probe that we use is redshift space distortions, or RSDs. This is a distortion that we see in the maps of galaxies that we observe because we do not have the radial coordinate of these galaxies. All we have is the redshift. And that is also affected by peculiar velocities in the distribution of galaxies. And what this causes is that on large scales, there's an anisotropy in the clustering of galaxies, in the correlations of galaxies. And we can use the strength of this anisotropy to learn about the growth of structure in the universe. So also from SDSS, we have these measurements of redshift space distortions over a wide redshift range. And again, divided here by the prediction from Planck in a lambda CDM universe. And the agreement is again very, very good. Okay, so let me tell you about the instrument. And I will see if the video works. We tested it before and it worked, but let me know, please, if you cannot hear the voice.
Light first reflects off of the telescope's 15-ton primary mirror, then onto its 6 large lenses that ensure DESI maintains a wide, highly focused view of the sky, covering an area about 38 times larger than the full moon. These lenses are housed in a device that can be adjusted within millionths of a meter to preserve the alignment of those lenses. After passing through the set of lenses, the galaxy's light reaches fiber optic cables in DESI's focal plane at the top end of the telescope. 5,000 robotic positioners, each carrying a single optical fiber, are programmed to move to pre-selected sequences of galaxy targets. This automated dance of robots allows DESI to target sequences of thousands of galaxies at a time. The optical fibers, which serve as DESI's eyes, send the galaxy's light down the length of the telescope to 10 spectrographs.
Okay, great. So I used to give this content basically using these extra slides, but I think these videos are so much better. So apologies if someone feels a bit strange that I'm showing a video within a talk. But let me just show you also here. I had another plot here. You can see myself next to the optical corrector. It's a huge corrector that is hanging from the top of the telescope. And it was aligned at UCL, where I used to be a lecturer at. And I also want to point out that there's these GFA cameras, these guiding focus array cameras that were made at IFI, my current institution, and allow DESI to also to point on the sky and to make sure that we are in focus and so on. Right. So let me give you an overview of the survey. So the idea is that we will use 5 different targets to get a very wide redshift range, study the universe between redshift 0 and redshift 4, with a total of 40 million redshifts. So this is more than an order of magnitude increase over eBOS or BOS, for instance. So at low redshift, we use what we call the bright galaxies, the bright galaxy survey. Those are galaxies that are nearby to redshift 0.4 or so, and we can use them even when the observing conditions are not great. So whenever there's a little bit of contamination from the moon or a little bit of clouds, we can still look at these nearer galaxies, and there will be 13 million of those. So it's a huge density of galaxies. Then in order to go to higher redshift, we will also use the luminous red galaxies and emission line galaxies. And then those will also overlap with quasars that we also use as tracers up to much higher redshift. And then above redshift 2, as I mentioned in the previous slide, we will also use the Lyman alpha 4s, these absorption features in the spectra of very high redshift quasars. And that will allow us to study the expansion of the universe at much earlier times. Right, so I added a couple of fun slides just to show how bumpy the road to dark energy can be. And I guess maybe the talk in Euclid also had some bumps, but we also had our share of bumps. So everything started great. In October 2019, we had first light. We were all very happy, very thrilled to see how well the spectrographs were working, everything, all the positioners. We were able to have hundreds of fibers focused on this M33 galaxy, one of our neighboring galaxies. And the quality of the spectra was just great. So we started commissioning, we started survey validation in early 2020, but as you probably remember, something happened in 2020. I was actually at the telescope when COVID started. Luckily enough, I was able to fly back with one of the last flights before the lockdown. But COVID, I mean, it had a massive impact to everyone's life, but it also had an impact on DESI. We were shut down for more than half a year. And for many, many more months, the whole collaboration had to work with different conditions because of that. But we went through that and we started doing recommissioning again. We started survey validation again in early 2021. And in May 2021, we started what we call the main survey. So the progress was really, really good. Even from the early days, we started covering wide areas of the sky. Then we started going deeper around the equatorial area to have a denser part of the survey. And this is how it looked after 1 year of data. This will be similar to the analysis, the first cosmological analysis that will appear in next year. They will also use a footprint similar to this one. So everything was working great. And then we had a collaboration meeting in Berkeley in June in 2022. And we were preparing that meeting. I was about to fly to Berkeley when I heard about a fire that was getting closer, and getting closer. And it got really close to the telescope. This taken from the webcam of the Mayal telescope. And I remember we were all in Berkeley refreshing our browser. And at some point, the webcam went down. And honestly, most of us thought that the telescope was burning. But luckily, it was just the power that was burned, the power cables. So the firefighters were able to keep the telescope safe. Other telescopes were not as lucky. And some of the telescopes at Kitt Peak were seriously damaged by the fire. But we went through that, and we had a fairly smooth sailing for the second year of data acquisition. A couple of months ago, though, pirates attacked. There were a cyber attack at the Magellan telescope that basically caused that the other telescopes that are controlled by Neuer Lab were disconnected from the internet, and that caused us some impact in the survey operations. Mostly, it's difficult to run a telescope remotely without internet, so we had to rely a lot on the people there and do things a little bit different. But as I mentioned, the good news is that in spite of COVID, fire, and pirates, the main survey of DESI is already 50% complete. And I think this is great to both this is thanks to a great instrument and a great survey operations team. That means that even though we had all these problems, we're still 3 months ahead of schedule. So you can see it on the right that the number of unique spectra we have already obtained in DESI is growing very fast, and we are about to hit the 25 million milestone. So during this talk and the next talks, you will hear about some terminology that we use in DESI that I think it's useful if I mention it here. So you will hear about the early data release, or EDR, and this is the data that was taken during survey validation. So it's not even in this plot. It's before we started the main survey. We had a few months of survey validation, and this data was made public and is being used for people outside the collaboration as well for some science. DESI M2 that you will hear later in the talks, because they were allowed the first measurements of BAO from DESI, are these they are 2 months from this narrow window from the moment we started the survey to the first engineering upgrades. So just with these 2 months of data, we had an amazing data set that we can use for cosmology. Then year 1 will be the first cosmological results. The true cosmological analysis will come from the year 1 data set that will basically include all the data until the moment of the fire. So after these ones, we will have DESI year 3 and finally DESI year 5 that will collect the 5-year survey until mid-2026. So just to finalize, let me tell you about the data that is already public. So first of all, before we can do DESI, what we had to do is to image a very large fraction of the sky. So DESI is a third of the sky, but the imaging survey that we used is actually wider than that. And we had many hundreds of nights of observations in 3 different telescopes. And we combined all this imaging together with infrared imaging from the All-Sky WISE telescope to provide the target selection for DESI. And all this data has been public for a couple of years now. You can find it in this legacysurvey.org website. And the first spectroscopic data were released last June in the early data release. This is over 1 million redshifts and also lots and lots and lots of stars. So if you're interested in this data, please go ahead. You can either go to this website or just Google DESI EDR, and you'll find all this very rich data set that is for everyone to play with. So just to summarize, I think it's great that DESI is observing at full speed. We are already 50% complete. EDR has been public for a while now, and we do hope that a lot of people play with this data. And as I mentioned, the first cosmological results should appear in less than a year, so please stay tuned for the cosmological analysis of DESI year 1. And if you like spectroscopic surveys, you should also know that we're already planning for the next experiments. We're working on an extension of DESI that we internally call DESI 2, and you might also have heard about SPEC 5, the next generation spectroscopic survey. So that's it. Thank you very much, and I'll be happy to answer the questions if you have them.
Great. Thank you very much. That was an excellent overview of the survey, the instrument, and what data is available. Does anyone have any questions about that? Please put them in the Q&A if you do. Maybe I'll throw you a softball question. So what are your interests within DESI, Andrea? What are you most excited about coming, or sorry, let me rephrase. What are you most excited about in the year 1 analyses?
I mean, the year 1 analysis, we will focus on the measurements that we know we can robustly do. So for instance, we'll measure on BAO and we'll measure on redshift space distortions. And this is great because it's going to be like significantly better than the current state of the art from SDSS. What I'm also excited about is what we can do besides those. So in particular, I'm excited to try new techniques on the Lyman Alpha Forest dataset. And Naim Karakaili later on will talk a little bit about this dataset and some of the cool things that we can do. But yeah, so I think the new techniques that we can apply with this data, it's also very exciting.
Great. All right. Maybe we should move on to Jean-Guy.
Stop sharing.
Yes. Thank you.
Okay. Yeah, you can see my screen, right?
Yep, looks great, and we can hear you well. Please go ahead.
Okay. So, hi everyone. I'm Jong-in Moon. I'm a PhD student at both MPA and MPE. I'm going to talk about the BAO research with only DESI data on behalf of the DESI collaboration. Okay. Here are the latest BAO papers for DESI Galaxies and Limon Alpha forests. In the first paper, you can find the Galaxy BAO research, which already show compatible BAO precisions with the full bus survey, which is 5 sigma BAO significance with 1.6% precision. And the second paper, Gordon et al., presents the Limon Alpha forest BAO detection, which demonstrates 3.8 sigma BAO significance in agreement with the final EBOS research. The purpose of these works were to check the quality of the early DESI data, which can be an important milestone towards DESI year 1 and completed year 5 data. Also, we wanted to see if we can detect the BAO signals with only initial 2 months of DESI observation and the data observed for the purpose of the survey validation before the main survey. Furthermore, the other reasons are to validate the early DESI pipelines and forecast the year 5 data based on the early BAO research. At first, I will mainly explain about the BAO detection with DESI Galaxies. For this study, we used the first 2 months observation data, which were observed from May 14 to July 9 in 2021. We internally unblinded the cosmology of these early data sets to check the quality of data and to test the BAO pipelines, but we blinded the other data sets to avoid any confirmation bias for the DESI year 1 analysis. In this work, we only focused on LRG and BGS samples because of the completeness issue of the ELGs and the sham noise problem of QSOs for these early data sets. Here, the completeness means the fraction of assigned targets over the total number of targets per observed tile, while the full DESI survey will observe the tiles in 5 overlapping passes in average. But for this early data, the observed tiles do not overlap each other because they are mostly first pass tiles. So the completeness of all of the tracers are quite low, as you can see in the table. And additionally, during dark time, in order of the priority for the fiber assignment, QSOs, LRGs, and ELGs are observed, so the completeness of ELGs is the lowest. And the QSOs are too sparsely distributed for these early data sets. So from these 2 tracers, ELGs and QSOs, we couldn't get good enough results in this stage. Additionally, for BGS samples, we applied the magnitude cut to make the number density constant in the BGS watershed range. Here are the MOCs and covariances that we used for this study. We used 25 comparably realistic Abacus summing MOCs to validate the covariance matrices and 1,000 easy MOCs, not only to validate the covariance matrices, but also to use itself as a covariance. Because these 2 kinds of MOCs were calibrated to an earlier version of DESI LRG clustering measurements than the actual LRG data we used in this study. So the MOCs were only used for the validation purposes, and we decided to adopt the semi-analytical, semi-empirical covariance, the Roscarcy covariance, rather than the MOC-based covariances for our main BAO research. This covariance is fast to calculate, much more flexible than MOCs, and precise as MOC-based covariances. To construct this covariance, it only requires 2-point correlation function with jackknife adders and a random catalog. This assumes Gaussian correlation and rescale the sham noise amplitude using a rescaling parameter calibrated by the jackknife covariance. Also, it uses a random catalog for the survey geometry. So if you want to know more details about this Roscarcy covariance, please check Vilkos et al. And Roskovetsky et al. Before we apply these covariances to the observed data, we wanted to see whether Roscarcy covariance really shows consistent fitting results with the MOC covariances. So we did a validation test for the LRG sample by comparing the BAO fitting results on MOCs using the easy MOC covariance and the ROS-CAR-C covariance. As you can see in the figures, you can see that the scatters along the diagonal are quite narrow for both pre-reconstructed and post-reconstructed cases. So this test proves that the ROS-CAR-C covariance returns unbiased and consistent estimates compared to the numerical ECMA covariance. So we can safely proceed to calibrate the ROS-CAR-C covariance to match the real data clustering measurements and perform the key BAO fits on both LRG and BGS samples. We also did a BAO reconstruction efficiency test using the LRG sample. The significance and errors improve after the reconstruction for about 90% of the cases. And the data points are located at the edge of the distribution for detection significance and the sigma of alpha, which means we are in a lucky situation compared to other mock realizations. Here are our main BAO results for LRG and BGS samples. The left panels show the 2-point correlation functions and the BAO significance in the function of alpha of LRG samples, and the right panels show the figures of BGS. We could get the 5 sigma BAO detection for LRGs with 1.6% precision, and this result is same with the both tier 9 BAO detection, which have similar number of LRGs and smaller redshift range of the observation. And for BGS samples, we could get 3 sigma BAO detection with 2.6% precision, and this was also consistent precision with both tier 12 low Z samples. In this early stage, we decided to blind our cosmology, so we shifted alpha values by delta alpha, making the minimum chi-squared value of the post-reconstructed LRG is located at unity. The magnitudes of these required shifts were less than 1 sigma, so we can say that the results are consistent with our fiduciary cosmology. Using these early data results, we computed the simple Fisher matrix forecast of the LRG isotropic BAO scale. Using the post-reconstruction covariances for the early data, the expected year 5 data, and the best fit model we could get from this study, the Fisher estimates show a factor of 5.8 between BAO signal to noise inferred from the early data and the year 5 data. So we could estimate about 0.29% BAO precision for the completed year 5 data. So if you want to know more details about these early galaxy BAO results, please check Moon et al. 2023. We also detected the Lyman alpha forest BAO signals using the early DESI data. You can see one of the cases spectrum in the data set on the left side. We measured the autocorrelations of Lyman alpha absorption using about 90,000 quasars at redshift bigger than 2, and also its cross-correlation using about 150,000 tracer quasars at redshift bigger than 1.8. In the right panel, wedges of the autocorrelation functions are shown. We could detect the BAO peaks from the full range fit with a signal to noise ratio of 3.8 sigma. And as you can see in the right figures, that you can see the consistency between our measurements and those in EBOS year 16. So we can validate the quality of this data at an early survey stage. Even though we only used a small fraction of the final DESI data set, our uncertainties are only a factor of 1.7 larger than those from the final EBOS measurement. So if you want to know more details about the Lyman alpha forest BAO detection, please check Gordon et al. 2023. Also, for the systematics, we are testing different HLD models. Left panels show the plots with the BAO fits for different HLD models that we are testing. There are around 21 models, which include various HLD models, parameters, and redshifts. In the right figures, there are heat maps that the shifts of some selected HLD models are shown. The blue values show the shift in alpha, and the red values show the significance of the shift, when comparing the different HOD models. Through this comparison test, we are quantifying our systematics now. So from all of these BAO works, we could check that our pipelines to BAO detections work properly. And these works are great milestones to move on to the eventual DESI year 1 and year 5 data analysis to achieve the sub% BAO precision with the finer year 5 data. Thank you for listening to my talk.
Thank you very much. It's impressive what you were able to measure with 2 months of data. Are there any questions? People should feel free to post them in the Q&A. Getting a lot of virtual applause coming in. So I may ask you the same question I asked Andreu. Hopefully, yeah. So what are you most excited about for the year 1 analyses?
So for as I was a part of the Galaxy BAO detection, only Galaxy BAO detection project, I clearly want to see the cosmological parameter constraints for that's year 1 analysis.
Great. All right. I'm not seeing any questions coming in, so maybe we'll move on to the next speaker, and then we can always loop back with some Q&A at the end if questions come in. Thank you very much, Yonggain. Sam, please take it away.
Yes, can you hear me?
I can hear you.
My slides.
I see them. Please go ahead.
Very good. Yeah, hi everyone, and thank you to the organizers for the invitation and for organizing CosmoPalooza. Thank you, Anthony and Satya. My name is Sam. I'm a postdoc at the Institute for Astronomy at the University of Edinburgh, and today I have the pleasure to talk to you about cosmology beyond BAO on large scales on behalf of DESI. So I would like to start with this screenshot of an animation by David Kirkby, which shows the DESI blinded year 1 data, but only a wedge of 80 degrees times 5 degrees. So this corresponds to 1% of the sky area and 3% of the total footprint that DESI is going to measure in its full year 5 program. And it shows the bright galaxy survey, the luminous red galaxies, the emission line galaxies, the quasi-stellar objects, and also the Lyman alpha, which is in between. And there's also the CMB here. What I would like to highlight is that with this data set, we can actually see the 3-dimensional structure of the universe. So DESI, due to this, the spectrograph, we are really able to discover these filamentary structure and really use that to infer cosmology on large scales. So the most important quantity we use to determine the structure is the so-called 2-point statistics. And just for those who don't know, are not familiar with that concept, you can imagine as if you throw sticks of various lengths and various angles into the sky, and each time there's a pair of galaxies that have exactly that separation, you just count how often this separation and this angle occurs within this map, all right? So you can make a histogram of all the distances that all the pairs of galaxies can have. We call that psi of r and angle. So that's the 2-point correlation function. And there it has a Fourier correspondence, which is the power spectrum as a function of wave vector and angle. And this is the quantity we normally use to model. So how does this look like? We have seen it already in Yonggain's talk before. This is the Lyman alpha 2-point correlation function in different bins of mu and different bins of angle. Showing the DESI EDR plus M2 as data points in comparison to EBOS DR16. And here's a similar comparison for the other tracers, the galaxy tracers of DESI. also showing as data points only 2 months of operation without EDR, so only 2 months versus the colored bands, which are EBOS. So you see, we are getting close to the EBOS error just with 2 months of operation of observation, which is really amazing. So you also notice that here I'm showing 2 rows. So this is because here the angle depends is integrated out. The first row shows the monopole, like the isotropic component of the correlation function, and the lower row shows the quadrupole, the anisotropic part. Now you might wonder, why is there an anisotropic part, since the universe should be isotropic, right? But as Andrea already mentioned, there are 2 effects basically which lead to this anisotropy. One is we call the Alcock-Paczynski effect, which comes due to the fact that we have to assume a fiducial cosmology to convert angles and redshifts to distances. And if we assume the wrong fiducial model, this will lead this means that distance is parallel to the line of sight and perpendicular to the line of sight. Although they should have the same distance, they don't appear as being the same distance, given that the wrong fiducial model is chosen. And this will lead to a quadrupole component. The other effect that Andrea already mentioned is the redshift space distortion. So we don't see directly the position of galaxies, we only see velocities, redshifts, and we can link it to the Hubble flow. But we also see the velocity component due to the peculiar velocity of galaxies, which the part parallel to the line of sight makes the galaxy appear at a position where it is actually not. And this we also call redshift space distortion, and that leads to this anisotropy that Andrea already mentioned in this slide at the beginning. So if you look at 2 different fields here, I show you redshift space on the left hand and real space on the right hand. You see that there are these 2 components. There's a large scale squashing effect and a small scale finger of God effect is what we call that. You see these stripes, which comes from the virial motion in very high density clusters. All right, so the question then is, how do we model this full shape, not only the BO, but the full shape of these correlation functions? So the standard way we proceed is we start with the meta power spectrum template, which is calculated from class, for example, and that's our template based on the Planck cosmology, for example. Then we need to since we don't observe the meta distribution directly, we only observe galaxies. We need to assume a bias model to convert this meta power spectrum to a galaxy power spectrum. Then we need to include nonlinear corrections to that because the real universe is highly nonlinear. It's not only linear perturbation theory. And in the end, we have to include that we also have this anisotropy, and we need to make the split in monopole and quadrupole to include the RSD. Once we have that, we can compare our model to the data. We have the monopole and the quadrupole, and we have a few parameters. We call it the compressed parameters, which to scale the template and see what the impact of the distance dilation on the template when fitting to the data. And the isotropic component is basically given by a scale of the distance parallel to the line of sight and 2 times 2 power of 2 across the line of sight. And the anisotropic component is sensitive to the ratio between the parallel and the perpendicular component. So that's the vertical scaling. But we also have a horizontal scaling, the amplitude, where the anisotropy, the ratio between the monopole and the quadrupole, is given by the growth rate f, and sigma 8 just is an overall amplitude scaling. Okay, so we can measure these parameters alpha parallel, alpha perpendicular, and f for a given fiducial value of sigma 8. Okay, and then once this is measured from this full 3-dimensional map on a full range of redshifts, we can compare that to our cosmological models. And this is what has been done by BOS and EBOS. Here you see the parallel BAO, the transverse BAO, and the growth rate, F sigma 8, and how powerful this data set is in constraining extended cosmological models and really determining, no, it's not, we don't have a high value of curvature. No, we don't, W doesn't deviate much from -1, and so on. So this is really powerful test of the cosmological model. And of course, with DESI, we are doing the same. We are, with the year 1 analysts, we are going to do the same. One thing I would like to highlight in this talk is that here there's this data point, which is comes from Planck. And as I've said before, we use a template based on the Planck cosmology. And I have shown, and if I go back to this image, I have shown to you also the cosmic microwave background here. So one question that came up in recent years is, when DESI is coming out, can we actually constrain cosmological parameters without relying on this prior of the CMB and using just the galaxy survey itself? So the CMB gives us the angular power spectrum, and with that also a matter power spectrum, which we use as a template. But if we want to relax that prior, we want to see what does DESI tell us alone, then we have to use it in our model in a different way. Of course, you could just run class or camp for many different cosmologies directly to the data, but we want to preserve this step of compressing the data into these compressed parameters to allow for a model-independent or model-agnostic test of our of the universe. And what I've done in my work was to implement a new parameter called the shape parameter, where we with one parameter vary the shape of the power spectrum, and then measure that jointly with the other standard parameters. And we can then interpret these parameters in light of any cosmological model. Then, since these parameters have been obtained in a model agnostic way, and this is a plot in a paper where we applied this to EBOS data, and this as it's a blueprint of what we plan to do with DESI as well, and where we have measured this shape together with the other model agnostic parameters, and we see that these our shape measurements are in agreement with Planck, which is given here by the gray band, and we can then interpret this parameters in light of Landa's DM model, for example, and see that by including this shape in that interpretation step, we can have better constraints on cosmological parameters when we don't include the Planck dataset. And yes, so this formalism is also now being tested within the DESI collaboration. I would like to show here a plot by Mark Maus, who is testing different, comparing also different model pipelines on the Abacus simulations. So this in particular shows the Abacus test, where you see the open contours for one Abacus simulation corresponding to the volume of full year 5 of DESI data for LRGs, and the filled contours show the average of all the 25 MOCs, and this has a combined volume of 200 gigaparsec over h to the power 3. So this is really shows that the models behave very good and have a very small systematic uncertainty. And this shape fit compression that I've introduced before also captures the results that you would get if you would directly model everything from the first place. So I'm running out of time. There's plenty of other things going on in DESI to do beyond BAO on large scales. There's Lyman alpha full shape by Cuccheo et al. There's the measurement of equality scale, primary non-Gaussianity, relativistic effects, DESI cross-lensing. So there's many things going on that I don't have time to cover here. My take-home message is that really this 3D information delivered by DESI spectra allows us to probe fundamental cosmology in a model agnostic way, and it's really, we should appreciate having this 3-dimensional view from DESI. So thank you very much. I'm happy to answer any question you have. Thanks.
Thank you very much. That was great. If anyone has any questions, please post them in the Q&A. We have one directed at Andreu, so we may circle back at the end of the session if we have time to have him answer that live. I'll ask you the same question. So what are you most excited about with year one? I think I know the answer based on what's on the slide right now, but we'll see.
Yes, exactly. So I would really like to know what, when we measure f-sigma-8, how does the redshift dependence look like? Is there any hint that, you know, might point to something that we have not expected so far? And I think, yeah, that's the exciting thing about DESI, that even in year one, we can probably see impact of some dark energy models on the growth of structure or on the geometry. So yeah, that's really exciting.
Okay, great. Why don't we save the rest of the Q&A time for the end and see if we can circle back with some more Q&A. Thank you, Sam. Naeem, please share your screen. Take it away.
I'm gonna share screen. Slides.
Can see him and I can hear you. So
Okay, great. Everyone, my name is Naeem Karaçaylı. I'm a postdoc at The Ohio State University. We're talking about 1D alignment of forest. So I want to start with a simple picture of what I'm talking about in the first place. We have a quasar in the distance. The light coming from the quasar will be absorbed and scattered by the hydrogen gas in between us, and it gives us a bunch of absorption lines in the quasar spectrum. So this is the cartoon here. What we heard about 3D correlation functions and BAOs include all the correlations of these absorption lines, including correlations between different line of sights. When I talk about one-dimensional power spectrum, we ignore these cross correlations and only include or study the correlations within a line of sight. And obviously this transition line happens at the line of a transition, which is 1216 angstrom. So what do we get out of this 1D power spectrum? So I want to phrase everything from the global power spectrum. This is the plot from Planck paper. So the power spectrum quantifies the density fluctuations. If you have more of it, there's more fluctuations at that scale. And this is in Fourier space. So if you look at the x-axis, you go to left, small k values, you go long wavelength modes or large scale fluctuations. And the model, the black line, our current lambda CDM model, goes to 0, which means the universe is becoming homogeneous at large scales. And on this figure, this is the dark matter power spectrum, and different observables are converted back to our lambda CDM power spectrum. And I just put bigger plots here because the legend is kind of small. CMB goes from very large scales to reasonably small scales. The galaxy clustering, including BAO, is somewhere here between these scales. And when I talk about 1D line of a power spectrum, we are going to really small scales, down to a megaparsec and smaller. So first of all, the broad agreement of the model and different observables are amazing. It spans about 4 decades in scale, so it's a very long agreement. The other thing is that these observables are coming from different times of the universe. CMB is about, when the universe is about 370,000 years old. Galaxies probe the late universe when the universe is older than 10 billion years old. And with Lyman alpha, we are probing the universe when it was about a few billion years old. Okay, so that is the scale of things. And 1D, we are going to small scales. So what can we get out of this small scales? I'm going to highlight two things, one of the more, I guess, exciting topics that we can do. I'm going to use warm dark matter as a building basis for the second one, which is the sum of the neutrino masses. So in our current lambda CDM model, the dark matter is cold. So that is supposed to be a hypothetical massive particle. Then we can ask an actual question of, okay, what if this hypothetical particle had a mass that is not infinity? The way I intuitively think about this is that if the particle gets lighter, it's going to move faster. So if a thing moves faster, you cannot constrain it in a small volume. So these light particles will not be able to constrain in small enough volumes to form enough clumps. And I really like this plot from the Senor et al. From 2023. The x-axis is redshift from early universe to late universe. The y-axis is the cool part. It starts from the cold dark matter, which is the massive hypothetical particle, and goes to lighter particles on the y-axis. And if you look at the late universe here, you see all these clumps when the dark matter is a massive particle. As you go up, particle gets lighter. So you kill all these small clumps, and things become smaller, smoother. So since you kill density fluctuations, you're suppressing the power spectrum. And that is what you see on the left here. In P1D, we have this weird units of inverse velocity units. Doesn't matter, you can think about length scale anyway. The y-axis is the power spectrum with a warm dark matter with some mass divided by without it. As you can see, as you go to lighter, the red line, the suppression is bigger. And this analysis was done with a different set of spectra, and I put the DESI scales roughly for comparison. So DESI will be sensitive up to these K values. Okay, that was not immediately on our agenda. I'm sure somebody is going to try to do it with DESI data, but what is forecasted for DESI is the constraint on sum of neutrino masses. So neutrinos are particles, so they contribute to the metal content of the universe, but they're light, so they're not massive. And the physics is similar to what I just described. You're replacing some heavy dark matter particle with some light neutrino particle. So things are going to move faster. So the small clumps are going to get killed by this fast moving particles. The effect is again a suppression in power spectrum. And that is what's shown here. It turns out the way you do this, you level your power spectrum with some CMB amplitude from large scales. You look at where line alpha is sensitive, which is here. You see a suppression, and you can constrain the sum of neutrino masses, which was done by using BOS data and CMB. It's one of the best constraints, I believe, I'm not sure. An upper bound on sum of neutrino masses by 12 EV, 0.12 EV. And moreover, neutrinos can have two different hierarchies, the normal hierarchy and inverted hierarchy. In the case that the neutrinos have the normal hierarchy with minimal mass, that would be 0.06 EV, DESI will be able to rule out this inverted hierarchy by 2 sigma. So our constraint on DESI, which is 0.02 EV, is very ambitious and in a way scary in terms of analysis. So this is the part I'm really excited about DESI in the future. And the rest of the talk is about the early data analysis and the things we discovered in terms of what can go wrong in the data. So early data comes with an asterisk, and Andrew fortunately mentioned what that asterisk entails. We have a survey validation spectra, call it 1% survey, or sometimes SP3 in terms of internal releases, that gives us about 7,000 quasars. We didn't find that enough to do enough statistics and analyze the data in a way we wanted, so we added 2 months of the main survey, that is M2, and main means normal operations of DESI. So SP3 is observed in very special conditions with certain targets, but M2 is our normal operations. And in total, our early data analysis had about 55,000 spectra. And I put the outline of the paper here. I'm not going to go through everything of the paper here, but there is a good description of what the method is, detailed tests about validations and systematics. And I just want to highlight 1 or 2 systematics here. So this is a quasar spectrum from DESI. This is a pre-year 1 spectrum. Internally, it's called iron. It's beautiful. You see the Lyman alpha emission line of the quasar. You see the carbon 4 emission lines, etc. You can even see the quasar continuum nicely. And the Lyman force is very clear to the left side of this emission line. And to the right, you don't see anything. And that is because any light emitted at these wavelengths will be redshifted away from the Lyman alpha transition line. We can find the redshifts of the quasar and the force pretty easily by just dividing it by our tracer redshift. However, the typical DESI spectrum looks like this. So that was very beautiful. We see everything. In this spectrum, we still know it's a quasar because we see the emission lines clearly, but we don't see the quasar continuum as clearly anymore. And the Lyman force signal is basically buried under all this noise. So our challenge is going to become about this noise and related things. So I'm going to start with the good news and go into the challenge later, obviously. So we had 2 different analyses of P1D estimation within DESI. One is led by me, the other one is led by Corentin Ravo. I'm using something called the quadratic estimator. It is the statistically optimal estimator, and Corentin was using the FFT estimator, which is a different way of handling things. The good news is, if you look at this plot, the blue and the orange, which are DESI measurements with 2 different estimators, agree pretty well. So we are confident in both of our analysis. The bad news starts from here. The black line is our bad news. It's the EBOS measurement from previous data set, and there's a clear discrepancy between the 2 data sets. So here we don't have a good sense. We have some ideas where this be coming from. We tried a bunch of things. We tried, the systematics I will tell in a minute, but they don't seem to be explaining this discrepancy. So this is going to be one of our challenges. The other challenge is we don't immediately have a cosmology, so we are actively trying to build a cosmology pipeline for these measurements. Okay, so what were the two major challenges we face? One of them is, as I said, it was the noise. Our signal is buried under noise. The second one is hard to see in a spectrograph, in a spectrum, but it's about the spectrograph resolution. So normally you would expect, a line, the atomic transition line, to be a sharp feature, but there is a thermal broadening due to thermal motion of this gas. So in this cartoon, I'm showing this as going from blue to orange. This orange line will go to the spectrograph and will get even more broadened out by the spectrograph itself. That is the green line here in the cartoon. The challenge with DESI is that this spectrograph broadening is about 5 times larger than the thermal broadening. And the thermal broadening has some physical information in it. So what we do is we deconvolve our spectrograph window function to remove its effect. That means we need to be really certain about our spectrograph window function up to high accuracy to be confident about deconvolution. And actually, we're confident up to % level, but even that % level confidence, it turns out, propagates to statistical errors quite a bit. As I said, we didn't have cosmology, so I had to do a simple fitting analysis. I'm just fitting an amplitude and a slope and running to the Lyman alpha power spectrum. There's no cosmology here. It's just 3 parameters simple fit. And I'm looking how much our error bars increase on this fitted parameters. And the upshot is this very bold red line to the bottom. If we add all the systematics, these parameters nearly get dominated by our systematics in terms of, error bars, which is a little unfortunate. That means we'll have a lot more work to do. Early data, we had 55,000 quasars. In our initial year 1 sample, we already have more than 400,000 Lyman alpha quasars. That means our statistical error bars are going to be tiny. So that means we need to really look into our systematics. And noise and resolution seems to be the 2 major sources in terms of instrumentation. And there is a plan that I can talk, if there's any question, I can try to describe it a little more. There is a plan to reduce the systematics. We can do multiple signal to noise bands. We can split the data into fibers or spectrographs, etc. I think I want to just wrap it up now and I can take questions. The summary is DESI is going to constrain some of the tuna masses very precisely. That's the statistical forecast. And I show the P1D measurements from the early data, identified 2 major sources as systematics, which is noise and resolution. Unfortunately, even with early data, we are dominated by the systematics errors. And there's a plan to reduce these errors, and I'm happy to take questions. But before I wrap up, I want to thank our sponsors.
Thank you, Naeem. If anyone has questions for any of our speakers, including Naeem, please post them in the Q&A. I will not ask you the same question as the others because you answered it in your talk. But a question I did have is, was your analysis of the early data blinded? And if so, how?
No, we don't do blinding. So P1D so far is technically not a called key project, so we don't have to blind. And EDR, we definitely didn't blind. There is a question if we should blind for year 1 analysis, but then that's another discussion point that we don't,
Okay. And then another question came in. Are the noise and resolution on slide 11 only for Lyman alpha, or do people also need to worry for other samples, including the quasar sample for clustering?
I don't think clustering will be affected as much with this because since with Lyman alpha, we're directly working with the flux values per wavelength, like right out of the pipeline almost. We are really sensitive to what the pipeline says in terms of what the noise is, what the resolution is. But clustering just needs a redshift most of the time. So that redshift is usually very robust.
Okay, thank you. And you stated that there's this complex issue of deconvolving the instrumental effects versus the thermal effects, one being physics we're interested in, one being sort of systematic. Is it clear that is it clear whether that is more of an issue on the DESI side versus the EBOS side when talking about this discrepancy? Or
So
is that
this
still
effect usually, in terms of where I think this effect, like the resolution itself, should be dominant, is these values. So that the resolution will definitely change things at the right end of this power spectrum plot. In terms of EBOS, I think, so DESI has a higher resolution than EBOS as far as I know. So in terms of that, we are able to go to higher K values. But if you're asking about how stable our resolution estimates are, I think they should be pretty stable, but I don't have a good sense of how it is compared to EBOS.
Okay, thank you. Now broadening it to all of our speakers, there was a few questions, one specifically to Andreu. He already answered it in the chat, but I'm wondering if you want to say a few words out loud about it, if you're still around. Yes.
Which one in particular? The one about the other surveys, or the one about DESI 2 and Spec 5? Or
so yeah, if you could elaborate on the upcoming surveys, DESI 2 and Spec 5, what are the goals of these surveys and how are they different from DESI 1?
right. So I mean, as I mentioned in my talk, in DESI, first we had to do this imaging survey that we call the legacy survey, right? To do the targeting afterwards and so on. And we got a lot of nights in very good telescopes to do that, but there's going to be LSST. And it would have been so much easier if we could have done DESI after LSST, because it will have an amazing quality, super deep imaging over a very wide area. So an spectroscopic survey using LSST as a targeting, it's like a no-brainer. Like someone has to do that. So that's one of the motivations. The other motivations is that we have been thinking of ideas of observing galaxies at much higher redshift. So DESI is observing galaxies only to redshift 1.6 because we need to detect the oxygen doublet, and that limits the redshift range that we can cover. But if we have other ways of detecting very robust redshifts in a fast way, then we can go to higher redshift. And we are exploring different ways of doing this, and it looks very promising. So the idea would be to extend the galaxy survey to much higher redshift using LSST. That's for DESI 2. For Spec 5, it's basically a generic word for all the ideas, some of them crazier than others, for what to do in, say, 10 years from now, or 5 years from now, 10 years. Thanks.
Okay, thanks. And then if anyone wants to tackle this, can any of our speakers elaborate on how DESI will compare with other sort of large spectroscopic surveys, such as Foremost, PFS, Euclid, in at least forecasts of constraints? Maybe Jiangyin?
So yeah.
Are you familiar with the sort of BAO measurements of the various surveys?
So for the there's a survey which is name is HATDEX. They are I'm also the part of the survey, and they are observing the Lyman ARPA emitting galaxies as DESI 2 is planning to observe. So I think they can have the synergy for that. Before for the targeting of the LAEs of the DESI, HATDEX can be kind of helpful for that.
Great, thank you. Does anyone else want to maybe speak to synergies or competition between the surveys? Healthy competition.
Yeah. So in terms of non-BAO science, I would also think more in terms of synergy rather than competition, because each of those have very like they have their own strengths. And for example, Euclid, as I with everything Andreu said, so Euclid has their own lensing and spectroscopy, so it will be they will extract a lot of power from combining these. Of course, there's the issue with the spectrograph, that they don't have fiber optics like targeting each galaxy individually, but they have this slits, right? Peter Taylor mentioned that also in his talk on Euclid in this conference. So yeah, I mean, there are different challenges and different things to figure out in all these collaborations, I guess. And we, in the end, we will see like which survey delivers the best constraints in what specific area.
Certainly as a community, it'll be beneficial to have these very different approaches to the same goals and seeing whether the constraints agree, which would obviously improve our confidence in the various measurements. So great.
Yes.
We are right at time and we have exhausted the Q&A. So I want to thank the DESI team again for giving these talks. It was fantastic. And I want to thank all of you for calling in. And this will be the final session of CosmoPalooza 2023. So thank you all for attending the sessions and we will see you next time. Bye.